Hello there, my name is Gustavo Colares. I'm from University of Santa Cruz do Sul in Brazil, and I'm here today to present you our study named Life Cycle Assessment of Plastic Packaging Film in Flexographic Printing. Today, it is estimated that nearly 80% of customer buying decisions are made based on the product's packaging. In this sense, customers are getting closer to the sustainability issues and thus are more often making decisions regarding the best option to be purchased. For example, if a certain product is derived from fossil fuels or from a renewable source. Therefore, it became very important to inform the customers the environmental impacts of the entire life cycle of the products, including its packaging and other production process. Concerning the food industry, large groups have applied the life cycle assessment or LCA in their process, aiming to identify and evaluate the environmental sustainability of their products. The Nestle Group, for example, took actions to reduce the associated impacts of their product named Dolce Gusto. Since its launch in 2006, the carbon footprint was reduced by 32%. The amount of non-renewable energy was decreased 41%, and the overall water consumption was reduced by 25%. In this context, our study aimed to evaluate, using a case study, the life cycle of plastic packaging through the flexography process on an industrial unit located in the south of Brazil. The environmental assessment differs from the others by considering and discussing the contribution of each of the fabrication stages in the product footprint, therefore facilitating the visualization of the most critical aspects and the improvement of target points. Regarding the objective and scope, this study selected gate-to-gate as cutoff criteria for data collection. Our objective was to apply the life cycle assessment methodology to identify and evaluate the main environmental impacts associated with the plastic packaging fabrication by flexographic printing process. The methods Impact 2002 Plus and Recipe Midpoint were used in CIMA-Pro software version 7.3.3. The functional unit was 1077 square meters of plastic packaging impression, which led us to a material flow of 1000 kilograms. Each package had an area of 0.07 square meters and a mass of 0.065 kilograms. The evaluation was carried out mainly with characterization. Figure 1 presents a summary of the plastic packaging process in flexographic printing, as well as the defined borders for the present study. In this process, the following stages were included: printing, verification, metallization, laminating, rewinding, and printed package. For each of the stages, inputs and outputs in terms of energy and materials were identified and also quantified. Here we can see Table 1, which presents the inventory associated with the elementary process and the adopted database. In the input for the printing stage are indicated the PET film, acids and other solvents, as well as electricity. For the metallization step, we can verify the presence of aluminum and other materials, as well as water and electricity. For the lamination, were considered polyethylene, stickers and electricity. In this slide, the outputs for each of the process phases can be seen. The considered materials were waste PET film, waste cardboard rolls, waste aluminum packaging, waste iron packaging, and VOCs emissions. It is important to highlight that the data from Table 1 was all inventoried directly in the monitoring of a real industry scenario. Here we can see Figure 2, which presents the normalized environmental impact categories according to the recipe midpoint and the Impact 2002 Plus methods. It was verified that the impact categories that had most points were, in this order: photochemical oxidation formation, fossil depletion, human toxicity, freshwater ecotoxicity, freshwater eutrophication, non-renewable energy, and climate change. In Table 2, we can see how much each of the impact categories represented, considering the total of 5.87 points. The photochemical oxidant formation, for example, presented about 28% of the total, followed by human toxicity and fossil depletion, both with 18%. Next, we can see that the freshwater ecotoxicity, non-renewable energy, and the climate change impact categories with 80.6, 7.67, and 7.1%, respectively. Figure 3 presents the impact categories in terms of percentage characterized. It is noted that the printing process, in this figure represented by the blue color, contributes the largest share to all impacts, and much of this characteristic is due to the PET film production chain. When looking at Table 3, it can be seen that the fabrication of 1,000 kilograms of film packaging contributed with almost 3,000 kilograms of carbon dioxide equivalent. This leads to a ratio of 2.875 kilograms of CO2 equivalent for each kilogram of printed packaging produced. In Figure 4, it is presented the contribution of each of the process stages regarding the climate change impact category. Printing process accounted for nearly 66%, or, in terms of CO2 equivalent, 1,896 kilograms. From this point of view, 1,398 kilograms of CO2 equivalent are from the PET film production chain. The electricity, on the other hand, accounted for only 13% of the total, 247 kilograms of CO2 equivalent. The lamination process contributed with 26% on the climate change category, and it can be seen that 91% is associated with the PE film production chain. In addition, Figure 5 presents a comparison with other studies on the climate change impact category. We can note that, on average, other authors obtained less CO2 equivalent emissions than the present study. Figure 6, on the other hand, presents the contribution of each of the process stages concerning photochemical oxidant formation. The contribution was 81 kilograms of non-methane volatile organic compounds, and 95% to the photochemical oxidation formation impact, due to the release of VOCs during the printing operation. In this slide, we present you Figure 7, showing each of the process stages' contribution for the freshwater ecotoxicity impact category, as well as Figure 8, which presents the contribution for each of the process stages, but for the non-renewable energy impact category. The substances causing the most impacts are manganese with 62 kilograms of dB equivalent or dichlorobenzene equivalent, and arsenic with 17 kilograms of dB equivalent. The same characteristic is observed on freshwater ecotoxicity impact category. For the non-renewable energy impact, it was observed a contribution of 68,000 megajoules. The elementary process of printing and lamination were responsible for the largest shares, which are 55% and 41% respectively. From the obtained results, it was verified that the printing process had the highest contributions to the 7 categories studied. Most of the impacts are associated with the PET film production network, the energy matrix used, and the production chain of the components of the paints and the solvents. The lamination and metallization process had lower environmental impacts. However, they are not negligible. In the first case, the PE film production chain and the adhesive are shown as critical points. In the case of the metallization, all contributions are linked to the aluminum production chain.
Overall, the highlight was the formation of photooxidant particles, representing 28.40% of the total points, to 11 categories of the tested environmental impacts. This profile is due to the release of VOCs during operation. It is recommended, in this context, for future research to environmental assessment of VOCs recovery scenario in the flexographic printing process. In this sense, based on the observed critical points, the future studies must focus mainly on this parameter control. Thank you all for your attention and feel free to contact me if you have any further questions. Thank you.